Thank you. I'll begin with a prayer. Dear Father, we thank you for this day. We thank you for these students. Just pray that you'd just bless our time together, Lord. Help us to glorify you when we do this day, Lord. In your name I pray. Amen. So, let's see here. I told you guys, a couple of you, that I'd do it. Let me just make a hint before I forget, because this one's kind of dastardly. Number 20, section 8.2, number 20. Here you face the integral of x cubed e to the x squared dx over 1 plus x squared. I go to Dr. Majerick and I'm like, have you seen this integral? And he's like, oh, that integral. So yeah. But anyway, I will not work it for you, but what I'll tell you is what you do is if you put w equal to x squared, all right, make the substitution w equals x squared, then look for an integration by parts to finish it. The integration by parts is not entirely obvious, but with that guidance, you should be able to get through it. All right, that's a path through the wilderness. Yeah. I
did it a much more complicated way. So
there may be other ways to do it. There usually are. Let's see here. And then, gentleman talked to me earlier. What's your name?
Prince.
Prince?
Yeah, yes, sir.
And which one did you ask me about?
Question about, yeah, it was 12.
Number 12 in
12 in the homework.
number, which section was it?
As long as this.
It's 5.7, number 16.
5.7, number 16. Why is it still so hot in here? It's driving me nuts.
Yeah.
All right.
That's rough.
Number 16, 5.7.
Yes.
Ah, yes. So I'll just go ahead and work this for you guys. Actually, let me work number 15. It's almost the same thing, right? If I work number 15, you should be able to do 16. Am I right?
Yeah.
So number 15 of section 5.7, very similar to number 16. It's x squared minus 3x plus 2 divided by x plus 1 dx, integrate. You know, that one's, I was about to say it's too easy, but I'm wrong. If this was x minus 1, then I'd be like, come on. You know, yeah, then you just factor, right? But this, not quite so easy. So the way to do an integral like this, when you have the numerator has a larger degree than the denominator, various techniques, but one I like is just long division. So here we go. So x squared minus 3x plus 2, and we're dividing x plus 1 into that. So I put an x times x plus 1 is x squared plus x. I subtract. That gives me minus 4x plus 2, right? So then I go, okay, so to get this minus 4x from x plus 1, I subtract 4, right? That gives me minus 4x minus 4. Then I subtract again, and that gives me 6. That is the remainder, right? The remainder is 6. And what does this mean? It means that this expression is actually equal to x minus 4, right, plus 6 over x plus 1. So after the long division, we go from something that we don't really know how to integrate, unless we just got, I mean, probably not. I mean, I don't know. There are other methods to do this also. And there's always another method, you know. But this is a method that's pretty good. And then once you get to that, we can integrate, right? What's the answer? there you go. This piece right here, I made a u equals to x plus 1 substitution, right? Where du was equal to dx, so it was kind of boring, but that's behind the scenes there. Any questions about this kind of integral? Let me do another one that's kind of like this, but not the same. How about this? What if I had the integral of x dx over x minus 5?
Can you use u sub?
What would you think u equal to?
Use x, subtract 5, and you solve for x.
So u equals to x minus 5?
Yep.
All right, very good. Then x is equal to?
U plus 5.
Right. So this is actually the integral of u plus 5 du over u, right? Which is the integral of 1 plus 5 over u du, which is u plus 5, natural log the absolute value of u plus a constant. And then I need to go back to x, right? So this is x minus 5 plus 5 times the log, the absolute value of x minus 5, plus a constant. Very good. Yeah, so u substitution puts this into place. Now there's another way to do it. Let me show you my algebraic way to do it, once you guys have caught up with me. So I'm trying to take a few minutes here at the start of class to try to catch any questions you guys have about the material we've already gone over. Once we're done with this little part, then I'll dive straight into trig substitution and hyperbolic substitution and try to explain to you how that works. That's where we're going today. If you already watched the second video that I sent, then you'll be really bored. So sorry. Although maybe not too bored. I haven't actually watched that video. I just know what it's about. So if I inadvertently do the same examples, it's just because I'm a creature of habit. It's not like planning or anything. So anyway, are we good? You guys up to, you got this? Here's the other way we could do this. I'm fond of this other way. Integral x dx over x minus 5, right, is actually equal to the integral of x minus 5 plus 5 over x minus 5. I just added 0. Why did I do that? Because then I have x minus 5 over x minus 5 plus 5 over x minus 5. So many 5s. Just to emphasize what's going on here. Of course, that's 1, right? And so we just have the integral of 1 plus 5 over x minus 5 dx. And then that I can just integrate. That's x plus 5 natural log the absolute value of x minus 5 plus a constant. So kind of a different way of looking at it. If I have the same degree, numerator and denominator, sometimes I can play this trick. Make the numerator look like the denominator by adding or subtracting a number. I mean, adding 0, basically. So, we found two kind of different looking answers, right? Are these the same answer?
Doesn't the minus 5 go into the C?
Right, that's the way we should think about it, is they just, the answers just differ by a constant, right? The derivative of both of these answers is the same function because they just differ by a constant. They're quote unquote the same antiderivative. That's not quite accurate. They're different antiderivatives, but they're, the same indefinite integral. I mean, if you want to get fussy, maybe I should put a bar here, but whatever. Anyway, any other questions? Particular?
I
Yeah?
think you're going to answer it today, but it was the integral of sinh x over 1 plus sinh squared x.
Integral of sinh x over 1 plus sinh squared x, is that what you said?
Mm-hmm.
Dx. let's see here. So do you guys have any ideas? What's the trouble with letting u equal sinh x? What's du going to be then?
Cosh.
Cosh. We don't got a cosh, right? Or do we? Remember, cosh squared x minus sinh squared x is 1, right? So, in fact, cosh squared x is 1 plus sinh squared x. So this denominator is really cosh squared. All right, so what u substitution should we make to do this integral then?
Cosh squared.
Right. No, not cosh. Well, if we did cosh squared, we'd be in trouble because then usual song. What should we let u equal to?
Cosh.
Just cosh. Right. So u equals to cosh of x, then du sinh x dx. And so we got integral of du over u squared. Right? If I write anything more, I'll solve the problem, so I better stop. It's one of your homeworks, right? I don't want to deprive you of the joy, but that's a very significant hint, right? The rest should be routine.
Oh, 26.
Number 26?
Number
Yeah.
26.
5.9 number 48.
5.9, number 48,
Yes.
which is number 26?
Yes.
Okay, cool. So guys, any other questions? I'm very glad one of you came and asked me about this problem before class, because this threw me for a loop. Like, I haven't really been honestly stuck on a Calc 2 problem in a while, but this got me. I don't know why. It's just bad. Bad problem. I mean, it's good, but it's bad.
It's a good problem because it's a bad problem.
Yes, I felt alive after I solved it, so it's good. All right, well, now, you said something interesting. You said I was about to cover things like this. That's in fact not true. So trig, interestingly enough, hyperbolic substitution, trig substitution, it's not about doing these kinds of integrals. It's about using these functions to do other integrals. It's a little bit sneaky. All right, so let's see how that is. So I will now introduce you to two methods. I'm going to focus exclusively on the trig substitution for a while. Once we get at least a little bit comfortable with the trigonometric substitution, then I will turn the tables and start talking about hyperbolic substitutions. All right? So let me get about 2 or 3 examples under our belt, and then I'll tell you what a hyperbolic substitution is. So to start with, trig substitution. Trigonometric substitutions. So this is part of a larger program of implicit substitution. So for me, my fundamental understanding of it, it comes from keeping in mind certain basic algebraic facts. So there's 3 sort of major algebraic facts I need to keep in mind. Cosine squared plus sine squared theta equals to 1. Right? That's one identity that we know. Another one is what? How about 1 plus tangent squared theta equals to 1? Right? Oh, sorry. Yeah, that one, yeah, thanks. That, of course, harder to make true. Sorry. Now, we can also say secant squared theta minus 1 equal to what? Tangent squared theta, yeah. What else do we know? How about like 1 minus sine squared theta equals to? Cosine squared theta? All right, great. Let's see here. So I think actually in practice, these are really the things I use algebraically. And paired with these are some, let's see here. Let me write here, u equal to, tangent theta equals to x. What if I say, I'm sorry, let me write it around. X equals to tangent theta. I want to write it that way. X equals to secant theta. What happens if I do that? What happens here if I put x equals to sine theta? What does that say about x and about dx? So of course, 1 plus x squared equals 2. Secant squared theta, right? Here, x squared minus 1 is what? Tangent squared theta under that substitution. If we put x equals to sine theta, we get what? 1 minus x squared equals 2 cosine squared theta, right? So how about dx? In the first one, what's my dx? What's the derivative of tangent? Secant squared theta d theta. What's the derivative of secant? It's secant tangent, right? What's the derivative of sine? Cosine, yeah. All right, so these are the three most popular sort of generic trig substitutions. Now I'm going to mix it up a little bit past this, but these are kind of the baseline. Let me show you how this helps. And so here's a standard example, really the first example anyone should see about trig substitution. Integral of the square root of 1 minus x squared dx. So let me just run down the list for you. Use substitution doesn't help you. Integration by parts, waste your time. All right? So we're stuck. Except a new technique has entered the arena of battle. Trig substitution. Trig substitution, its chief goal, its chief aim is to remove radicals. All right? So by making the appropriate trig substitution, we can get rid of this square root. Let me show you how. So which trig substitution should we make? Well, this is like a 1 minus something squared inside the radical, right? So I make an x equals sine theta substitution here. So dx is cosine theta d theta, and 1 minus x squared is cosine squared theta. So what I have is I've got the square root of cosine squared theta, and then my dx is cosine theta d theta. Aha! But the square root of cosine squared is cosine. So I get cosine cosine, which is cosine squared d theta. Which is very nice because we already know how to do that integral, right? We already know that we say that that's 1/2 of 1 plus cosine of 2 theta d theta. And so this is going to give me theta over 2 plus 1/4 the sine of 2 theta plus a constant. And now I have to convert back to x, right? So if x equals sine theta, right? What's that make theta equal to? Inverse sine of x, but right. So here it is. Not the fanciest form of the answer here, but it's a decent answer. Inverse sine of x plus 1/4 the sine of twice the inverse sine of x plus a constant. Which I'm sure all of us would have guessed, right? If you want a function that when you differentiate, you get back the square root of 1 minus x squared. I mean, obviously it's this, right? Sorry, I just feel like it's necessary to insert that time so you can appreciate what we're doing. We're finding something that when differentiated, you get back to that. That's amazing that that is the case. This can be cleaned up a little bit. Like there's not much I can do to inverse sine of x, but this over here, I could do a little bit better. I could rewrite that as an algebraic function, all right? Let's see here. Let me try to do that. So this is a decent answer, all right? It's not the best answer, but it's not a bad answer. A better answer would come from converting, what's sine 2 theta? Two sine theta cosine theta, very good. Right, so 1/4 sine 2 theta is actually what? It's actually 1/2 sine theta cosine theta. And we can do better here by making a little triangle, which sort of explains what the substitution means. So sine theta is equal to x, right? But x is x over 1, right? So think of x as being the opposite side of the right triangle, right? And the hypotenuse is 1. What else is in this right triangle? What's the adjacent side? Not an accident that this happens. Right. Do you see where I mean, look, that's the thing we got rid of. So that tends to happen when you're making these little triangles corresponding to the substitution. The part you don't get will be the part you got rid of in the integration. But yes, that's what it has to be for the Pythagorean theorem to work. But once I have this triangle, I can write down algebraic functions for sine theta and cosine theta, right? Well, sine theta, what is that? Yeah, it's x. But cosine theta, what is that? Right, the square root of 1 minus x squared. So the point is that this ugly, ugly thing, right, is actually that algebraic formula. So I might ask you a question where I say, leave your answer in terms of algebraic functions as much as possible. So if those instructions are given, I want you to actually go through this thought process and try to remove inverse trigonometric functions wherever you can. There's nothing I can do about this 1/2 inverse sine. That comes from what I call a naked theta. It's just a theta sitting out there by its lonesome. There really isn't nothing, there's nothing you can do about this except write inverse sine x. I mean, it is what it is. But the other term we can improve on. Good? All right. You guys seem too comfortable. Let me make it worse. What if I was to say, example 2, integrate the square root of 9 minus x squared dx? So, like my basic table over here is in some sense a little bit too simplistic. Like I should have aimed higher. This is a very, very low-tech table. Like maybe what I should have written, well, it's too late. That's a baseline thought. We do better. There's a little bit more to think about here. So like this, I want to think about, I'm going to let x equal to 3 sine theta. And the reason I'm going to do that is that then 9 minus x squared is 9 minus 9 sine squared theta, right? So I factor out the 9, and I got 1 minus sine squared theta, right? Which is 9 cosine squared theta. Right? And my dx, well, what's my dx is 3 cosine theta d theta. So I'm off to the races here. This is the integral of the square root of 9 cosine squared theta. And my dx is 3 cosine theta d theta. So that's 9 integral of cosine squared theta d theta. We just did this integral a second ago. So I get 9 halves theta plus 9 over 4 sine of 2 theta plus a constant. Same integral. Multiplied by 9. Now what if I want to write my answer pretty as I can. So this time I've got myself a sine theta is x over 3. Right? Now, the trigonometry, you guys told me just a second ago, this is really 9 halves theta plus 1 half sine theta cosine theta, right? So I'll do that again. Well, sine theta is x over 3. We got that. What's cosine theta now? So we've got x is the opposite side. 3 is the hypotenuse in this triangle I'm drawing. What's the adjacent side? I take your answer and add a square root to it. But yes. Right? Not an accident. That's what we were trying to fix to start with, right? I mean, but now you can see what cosine theta should be what? Cosine theta should be square root of 9 minus x squared divided by 3. Okay, so let's put the pieces together here. That's 9 halves. What happens if I solve for theta? Inverse sine of? Right? This says theta is inverse sine of x over 3, right? Ugly, but I can't do better. And then this 1 half sine, oh, I'm sorry, I lost my 9. There was a 9 halves, right? Which is kind of neat because this 9 cancels with the 3 and this other 3 from the sine and cosine. So I get 9 over 9, and I just have plus 1 half x times the square root of 9 minus x squared, plus a constant, of course, and there you have it. That's about as good as I can do. Yeah.
So did you just get your x by going like if you squared it?
So there are 3 kind of generic patterns to look for, right? We have the variable squared minus a number, all right? We could have a number minus the variable squared, or we could have the sum of a number and a variable squared. These are the 3 kind of quadratic patterns that we can look for. And you either make a tangent, a secant, or a sign substitution, depending on which one you see. Since I've got number minus variable squared, I made a sign substitution.
And it's 3 sine because the square root of 9.
Right. Yeah.
It's probably a stupid question, but how did you integrate the cosine squared theta? From like, what's that?
Same as over here. So cosine squared is 1 half of 1 plus cosine 2 theta. Yeah. Yeah.
Do we just need to like memorize
Yes. Although I prefer you understood it. But yes. So depending on what you mean. Let's see here. Oh, how about this? Example 3. Keep asking the questions. Good questions. What if I have the integral from -1 to 1 of the square root of 1 minus x squared dx? What's this equal to? So we could go through the same argument as in example 1, right? It will not be 0. And we could get to the integral of 1/2 1 plus the cosine of 2 theta d theta, just like before, all right? And the thing is, if I have d theta here and I'm changing the bounds from x to theta, how would I change them? Yeah, I have to figure out, so sine of, so what I'm at, the question is, with u substitutions, we just plug in the x value into the u formula and it gives us the new u bound, right? But this is a little bit different, right? Because the new variable is theta. We're not saying theta equals blah, substitute. That would be like a u substitution, right? We're saying the old variable x is wrapped up in the new variable theta by a sign. This is an implicit substitution, right? A u-style substitution would be something like theta equals to inverse sine of x, right? But you don't want to do that. I mean, you wouldn't get anywhere doing that. So what the gentleman said is exactly right. We want to look for 1 equals to sine theta. That would be the upper bound, upper theta, right? And -1 is the sine theta lower, the lower bound for theta. So how do you solve those equations? Which theta gives you sine of theta is 1? Pi over 2. And how about -1? I'll take that and make that a minus pi over 2, but thank you. Right? Something subtle there. But you definitely want minus pi over 2. So then this integrates to what? Theta over 2, evaluated from minus pi over 2 to pi over 2, and then plus 1/4 sine of 2 theta, evaluated from minus pi over 2 to pi over 2. Now, how about this second term? It's going to give you sine of pi on the top bound. It's going to give you sine of minus pi on the bottom bound. What's sine of pi or plus, what's sine of plus or minus pi? It's 0. That piece doesn't matter. So this piece evaluates to 0. And how about this other piece? We get what? Pi over 2? Yeah. I'm sorry, we get, yeah, pi over 4, right? Minus a minus pi over 4, also known as? 0, no, pi over 2. Now, this question might well have been assigned to you by a malevolent Calculus 1 instructor because it's a reasonable Calculus 1 question, because this is the area bounded by the square root function, right? So that says x squared plus y squared equals to 1, and y is greater than or equal to 0. In other words, this is the area of the upper half unit circle, which is half the area of the unit circle, right? It's pi over 2. So sometimes Calculus 1 instructors will give this on the basis of the assumption that you know the area of a unit circle is pi. Because somebody told you, right? Not because you derived it. Hey, check it out. We just derived the area of half of the unit circle is pi over 2. It's kind of neat. Yeah? A little bit, maybe. Yeah? Would you like to see more? Yes, maybe. I'll leave this up here. I will get rid of this one. Yeah. Example 4, let's look at the integral of dx over the square root of x squared plus 4x plus I'm thinking. Let me think for a second. I'm trying to make it fun. Fun. 13. That seems fun. That's okay. I don't believe in that sort of thing. Let's see here. Although I will admit, I do find myself in the odd position of rooting against our football team going forward. I like to have class. So I have to root against the team. I mean, I don't want to, but this is the position I've come to. I mean, it's dangerous for us to win. Let's see here.
I think that's all.
It's a slippery slope, but only if we beat FPS top 10. I don't even know what that means, but okay. Let's see here. So what if? So this is, you see, this is the other wrinkle that I was talking about. One of the wrinkles is that that's too naive because I'm assuming that we've got no, it's like 1 plus the variable squared, right? Or 1 minus the variable squared, or the variable squared minus 1, right? That's too naive because we might need to have a multiplier. We might have like a 9, which means we have to do 3 times the trig function to pick up that 9 in the squaring, right? That's the one thing that could happen. But this is yet another wrinkle that we can deal with. What if we have something like this? Well, then we need to do what's called complete the square to make it look more like these patterns. So here's what we do. This is the square root of x plus 2 squared, right? And then what am I left over with? 4 plus what is 13? 9, right. So this is kind of like the third row. Oh, I'm sorry, I can't read. I need to put my glasses on. I'm sorry, my apologies. It's kind of like the first row. This is going to be a tangent type substitution. I want the thing inside the radical to become a secant squared, times a number perhaps. All right? What should I make the substitution then? How about this? X plus 2 equals to what? I want it to combine with that 9 and give me a 9 secant squared. That's what I'm seeing here. Yeah, tangent. How about 3 tangent theta? See, because if I do this, then x plus 2 squared plus 9 is what? It's 9 tangent squared theta plus 9. I can factor the 9 out. And that gives me 9 secant squared theta, right? So this is going to be integral. And what's dx? If this is my ninja way. Let's see here. Dx is what? Sorry, I watched too much Naruto. What's up?
Would that be 9 tangent theta plus 13?
Why?
Because you're squaring up 3 tan theta plus 2.
I'm not deriving something. I'm just suggesting x plus 2 is 3 tangent theta. If I make that substitution, then that squared, x plus 2 squared plus 9, gives me That's 9 tangent squared, that's plus 9. I factor out the 9, I've got 9 secant squared theta. I mean, you could...
I didn't see the plus, I thought it was x equals 3 tan theta for some reason.
Oh, no. The plus 2, yes. The plus 2 important. Now, dx doesn't even see the 2, right? We get dx is what? It's 3 secant squared theta d theta. Which is pretty nice, right? So then, so what we do here, we got, what's dx? Dx is 3 secant squared theta d theta. Downstairs, what we got? We got the square root of 9 secant squared theta. I warned you this day was coming. So square root of 9 is 3. 3 over 3, 1. And we have the integral of, oh yeah, that's right. To quote my son Matthew, that happened. Like anytime he does something he's not supposed, anytime something happens that's not supposed to have happened, he'd be like, it happened. It's like, it's not a reason. But it's a saying of Matthew. Anyway, oh well, poor Matthew. He got a splinter under his fingernail yesterday. So like, my wife took him to the doctor and was like, I can't get it out. And the doctor's like, yeah. So there's two options. We hold him down and I dig under his fingernail to get the splinter out. And then the doctor's like, I am not willing to do this. Right? The other is to send him to the hospital and have him put under. It's like, no, we're not going to have our 4-year-old put under for a splinter under his fingernail. That's okay. I don't think the doctor was recommending it either, but so poor Matthew. Yeah, it's bad. Like, it's just, I know, right? It just, well, the thing is, Isaac told him, like, don't touch that, Matthew. Let Daddy get it. And then Matthew stood there and did something, and I'm guessing in the process of that, he removed the part I could have taken the tweezers and pulled out with, right? By the time I got to him, it was all the way under. He bites his nails, so it's like, I don't know. So he's been ordered to soak his hands for a couple days. We'll see what happens. Probably nothing. It'll probably just get, like, it's very fine, you know. I digress. Okay, so I told you this would happen. I wasn't just integrating secant theta because I like secant theta as integral and I think it's neat. It comes up in tons of problems. It just happens. So how do we integrate secant theta? We worked that out the other day. I'm not going to work it out again. It is the natural log, the absolute value of secant theta plus tangent theta plus a constant. Yes, you should memorize that. Or learn to derive it if you have time. Now, we can do better than this, right? I want to write the answer as an algebraic function. So to write answer, what's an algebraic function?
Tangent theta equals x plus 2 over 3.
This is really complicated, guys. What's an algebraic function? It's a function whose formula can be constructed with rules of algebra. So basically, you have a formula which is constructed from powers, sums, and radicals, division. Polynomials are algebraic functions, for example. Rational functions are algebraic functions. The things we're integrating today, algebraic functions. Now, somebody said something before I was blathering on about uninteresting terminology.
Oh, I just said that you could say tangent theta equals x plus 2 over 3.
Ah, yes, very good. That is the secret, the keys to the kingdom, if you will. X plus 2 over 3. Now, once you write that, you should think, aha, triangle. So opposite side, x plus 2, adjacent side, 3, theta, and then what's the hypotenuse? X plus 2 squared, right? Plus 9, aka x squared plus 4x plus 13.
Is it always going to do that?
Yes.
Or is that just a coincidence?
It is not a coincidence. So log the absolute value. My secant theta, what's secant theta? That should be hypotenuse over adjacent, right? Which in this case is 1/3 the square root. I'll go back to x squared plus 4x plus 13 because, I don't know, kind of like it. And then what's my tangent theta? Oh yeah, 1/3 x plus 2 plus a constant. Oh, we could factor out 1/3 in the argument of the log, right? What happens if you have like log of 1/3 Pac-Man? What are the laws of logarithm? It's the log of 1/3, right? Plus log Pac-Man. So my point is we can factor out this third here and there, and we can rewrite this simply as the log of x plus 2 plus the square root of x squared plus 4x plus 13. Close. Actually, do I need absolute values here? And why don't I? It's more obvious if I rewrite this as x plus 2 squared plus 9, right? Exactly. It has to be positive because the magnitude of this root is always larger than x plus 2, its magnitude, which means this is always more positive than that is. If they're both positive, they add. If this one's negative, then this is still bigger, so it wins. Yep.
Take off if we do write the absolute value signs.
I mean, I don't know. I'd be happier if you didn't. Will I take off? I mean, I don't know. I mean, it kind of depends like how awake I am when I'm grading and other things. It's just hard to say. I mean, I want the best answer possible. So what's more likely is I give you a bonus point if you put it there. Yeah.
So where'd the 1/3 go?
So the point is, if I factor the third out, the log of 1/3 times something is log of 1/3 plus that log of something, right? So factoring the 1/3 out, then I get log of 1/3 plus c. So I just relabel c plus log of 1/3 as c bar.
Oh, so you just stuck it inside of the C.
So like this, the c bar I'm saying is log of 1/3 plus c. So I just absorb it into the constant.
So you could just add that at the end still though? It would be okay if we did that.
Oh yeah, yeah. If you have log of 1/3 plus a constant, that's also fine. Yeah,
So
same answer.
would it be that log of 1/3 multiplied or added to the end?
Added. Yeah, multiplied would be wrong. Now, of course, you know, this is like a larger point. I could also go over here and say plus, you know, 15, 3, 4, 5, 6, 7, 8, 9, 10. Oh, not 10, we don't do that. 9, 1, 0. Like that. Still an antiderivative. You can add whatever constant you want to the end. It's still... But, I mean, just... this is not interesting. Let me stop talking about this. All right. I think I've given you 4 examples of trig substitution, so it's time to... I mean, I guess we haven't gotten to the secant substitution just yet, have we? So, I'm not sure I'm going to. Did I? No, I did a tangent. I did a sine. I did a couple sines. I haven't done the secant yet. And forgive me if I don't do a secant substitution at the moment. I feel like the time is right for me to introduce the next concept, which is hyperbolic substitution. So example 5. All right. What if I had 1 plus x squared? Now, if I so chose to do a trig substitution, what would I do, and where would it lead me? So I would do what? I would say x equals 2. What is it? tangent, right? This is a tangent substitution. If we do trig substitution, I do x equals tangent theta. So 1 plus x squared is equal to 1 plus tangent squared theta, also known as secant squared theta. Now my dx is secant squared theta d theta. Yeah, I just gave a quiz in differential equations today that required the integral of secant squared. I wonder what I'm going to see when I look at it. How many people still knew the integral? Secant squared is tangent. There's usually, I tell you, I'm not kidding, there's usually about 40% of the DiffEQ students who've forgotten it. Something like that. It's kind of a bellwether for who actually knows any calculus. So, like, has any calculus stayed in their brains past the courses? Like, it fades. It really does. Anyway, I digress. So the point here is I've got square root of secant squared theta. Dx is secant squared theta d theta. Oh, ouch. 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 We can do it. I showed you how in the video yesterday, right? You found a way to fit it in between the partying, you know? But I think this was at like the 20-minute mark, right? We had to integrate. You have to integrate by parts. It also involves the integral of secant. It loops back. Yuck. Is there a better way? So we don't have to integrate secant cubed. So this is one of my primary motivating examples for why we should think a little bit, at least, about hyperbolic substitutions. All right? So hyperbolic substitutions, if I want to talk about the naive sort, they're all based on the fact that cos squared theta minus sinh squared theta is equal to 1, right? So one of the things I could notice is that, like, 1 plus sinh squared theta is equal to cos squared theta, right? So if I make a sort of a corresponding row here, if I put x equals to sinh theta, right, I get 1 plus x squared is what? One plus x squared will be cos squared theta, and my dx is what? My dx would be cos theta d theta. Now that's just the ticket for this example we're working right now. So let's turn that frown upside down and look at this as a hyperbolic substitution instead of a trig substitution because, well, trig substitution led us to a place we don't want to go. So if I put x equals to, what did I say? Yeah, sinh. What's dx? Dx is cos theta d theta. And as I was just saying, 1 plus x squared is cos squared theta. So this integral becomes the square root of cos squared theta, cos theta d theta, aka the integral of cos squared theta d theta. Yeah. Okay. Then the question is, how do you integrate cos squared theta? So let me just take 30 seconds to derive an identity for you guys. If we have cos squared theta, what is that? That's 1/2 of e to the theta, right? Plus e to the minus theta times 1/2 e to the theta plus e to the minus theta, right? It's cos theta squared. Multiply this out. What you got? You got yourself a 1/4 e to the 2 theta plus e to the minus 2 theta plus 2. In other words, hooray, 1/2 of 1 plus the cosh of 2 theta. So, now if you don't like this way, you could just convert it to exponentials and do that integral just the same. Doesn't much matter to me. But this is definitely an integral we can do without a lot of thinking. Certainly don't need integration by parts or anything too fancy to do that integral. We just need to know what cosh is. So this is what, theta over 2 plus 1/4 the sinh of 2 theta plus a constant. Yep.
How did you go from the second and third step?
Here to here?
No.
Well, the 1/2 of e to the 2 theta plus e to the minus 2 theta is cosh 2 theta. But I've got a quarter, so there's a half of that. And then 2 over 4 is 1/2. Yeah.
So are there more like hyperbolic identities that are just versions of trigonometric identities? Like
Yes.
that happening or again?
Yes.
Okay.
Almost anything you know for trigonometry, there is a hyperbolic analog. It is true. What's that? Inverse. There is an inverse cosh. Yes. Hush. Yeah.
I'm not calling them inverse trig instead of like the arcs.
I mean like the reciprocal ones? There's like a, I mean there's a, I don't even know how to pronounce this stupid thing, but there is this, yeah. The hyperbolic secant, yeah. Sech. Yeah. Or, yeah, that's 1 over cosh. But anyway, I digress. So let me put it back into algebraic functions. Not the best answer here, but a pretty decent answer. 1/2 solve for theta here. So we have 1/2 inverse hyperbolic sine of x plus 1/4 sinh of twice the inverse hyperbolic sine of x. Plus a constant, of course. Now, there's even analogs to the triangles we were writing for hyperbolic substitutions, but you got to be careful. They're not subject to a Pythagorean identity. They're subject to this cosh squared minus sinh squared identity. That's how you have to construct the hyperbolic triangles. It's a little bit subtle. So I'm a little bit worn out at the moment. I'm going to try to do it on the fly. Yeah.
I'm confused why we're rewriting it as an algebraic function.
Because algebraic functions are prettier and nicer, and it's a way for us to understand more about functions. And I mean, if you want a sort of coding reason, maybe you can easily code this formula. Maybe you've got a built-in log function, but you certainly don't have a built-in inverse hyperbolic sine function, right? But fortunately, we addressed this issue the other day because we learned that you can rewrite inverse hyperbolic sine in terms of a log of an algebraic function, right? So this can be rewritten as like natural log of x plus the square root of x squared plus 1 or something like that. We worked that out with we solved the quadratic equation in the exponential. I wrote down this list of identities. I do not have those memorized. I'd have to look at my notes for those. Back in chapter 5. Theorem 5.24 or something like that, but yeah. So these could be made into algebraic functions if we were willing to refer to that theorem and go through that. This one can't be fixed. Well, no, excuse me. Actually, I think this is a little bit different because this is inverse hyperbolic sine that could be made into the log of an algebraic function.